Hello students. So let's get started with this particular lecture. In this particular lecture, we will have a look at silicon as a material and why it is so important material for developing the CMOS transistors. There are some unique properties of the silicon which will be very useful for characterizing the CMOS transistors. And that's the reason why it has been very popular. So this is kind of a silicon with the duped, the phosphorus duped silicon atom structure. If you look into the silicon crystal lattice, we will have the silicon, and instead of this particular p atom here, we will have a silicon atom, right? So instead of, so let me take a pointer. So yeah, of course, the black one, and then yeah. So I will have a silicon here in the middle also, and then in the neighboring where it forms the covalent bond. So there will be silicon. So the neighboring is silicon as well as the central atom is silicon. So that's how the silicon crystal lattice structure will be looked. And so the silicon density is somewhere around 10 raised to 22. So that's what I've stated here, 5 into 10 raised to 22 per centimeter cube. So what it really means is if I take a 1 centimeter cube as a block of 1 centimeter cube, I will get 5 into 10 raised to 22. So roughly around 10 raised to 22 atoms of silicon. So at room temperature, if I apply, on that particular 1 centimeter cube block, if I apply a kind of an electric field, and let's say that, it's a very minimal electric field of 0.1 or 0.01 volts on the positive and then the negative potential. At room temperature, due to the thermal energy, there will be 1.4 into 10 raised to 10. So I'll roughly say that around 10 raised to 10 per centimeter cube, because we are taking the block of 1 centimeter cube. So roughly around 10 raised to 10 bonds, right, of the silicon atoms, which it forms with the neighboring silicon atoms, will be broken, right? So if I, if you can visualize the silicon atoms and then the bonds are broken, then that means I'll get the free electrons. And then those particular free electrons will be, if I consider this particular bond to be broken, so I will get actually the free electrons. So 1.4 into 10 raised to 10 such bonds can be broken, and thereby we will get 10 raised to 10 free electrons, or the majority carriers that will be flowing towards the positive potential, of course, because it's in electrons, and thereby we will get the current. But in 1 centimeter cube of the silicon block, if I actually get only 10 raised to 10 the electrons, the amount of current that it is going to generate tends to be very, very low. And that is not so useful for the circuit design applications where we want at least 100 or tens of microamperes, right? So in that case, to improve the conductivity, external materials, external elements called as dopants, have been are introduced. So that's a standard practice for the CMOS structure. So the overall, the dopants have been introduced to improve the electrical conductivity. Now in this particular example, I have taken an N-type doping. The N represents having, for the NMOS structure, that is why the N-type dopants are utilized here. The N also represents that we have an electrons, the negative majority carrier. So what it really means is if I have if I consider an element which has more than 4 valence electrons, so in this case 5 valence electrons is what I have mentioned here. It could be arsenic or it could be phosphorus, right? So the 5 valence electrons, if it is doped here, so this P stands for phosphorus. So this is an external material, external element here. P represents phosphorus, external element. So external element, or I can say that external atom. So if the phosphorus is duped in in a certain particular manufacturing techniques like the diffusion or implantation, so somehow we get the diffusion process done, and then we have this phosphorus diffused inside the silicon atom structure. We will have one phosphorus which forms four covalent bonds with the neighboring silicon atoms. But phosphorus has five valence electrons, so one more electron is available here. So in that particular case, this particular electron will now be available for it to be attracted towards the positive potential whenever the bias is applied. So if I introduced two more phosphorus atoms, I will have two free electrons, and that which we can utilize it for conducting the current. And if I introduce 10 phosphorus atoms, I will have 10 such electrons, right? So similarly, we can actually dupe the phosphorus in such a way that we can have more than 10 raised to 10 electrons, free electrons. So more than 10 raised to 10 electrons, so that I'll have more such electrons, and then I'll be able to make the transistor design highly conductive. So that is one advantage of, and that is one particular way of getting or extracting more current from the silicon substrate. Again, one of the important benefits of silicon is it is abundantly and easily available here. And that's what I've stated here. And hence has been highly utilized for the semiconductor circuits and systems. There have been different materials such as the carbon and graphene materials trying to be used as a semiconductor material, but it is still under research. And one of the advantages the silicon has is the abundant resources, and then because it's a semiconductor material, we can dupe it easily. Silicon dioxide has another dielectric, the oxidation, the process of oxidation, which consumes some of the silicon atoms and forms the silicon dioxide, is also an easy process. So if I use a different material altogether, like a carbon or graphene, if I try to oxidize the graphene-based oxide or the carbon-based oxide, doesn't form that kind of a dielectric. And dielectric is kind of very, very important for the CMOS transistor. So, having these properties of silicon, easily dupable, the dopants can be easily diffused inside the silicon atoms or the crystal lattice structure. The silicon dioxide is another advantage of the silicon material, and having a good conductivity extracted from the silicon material makes it widely popular as a semiconductor material. And hence the CMOS transistors or the CMOS design or the VLSI design in a broader sense is heavily dependent on the silicon material. So in the last slide, we had seen the N-type dopant where the phosphorus or the arsenic was duped inside the silicon crystal lattice structure. So here is an example of the boron, where boron are also dopants having the 3 valence electrons. So that will give us one particular hole. So let me pick up a pointer. Again, I will use black. So if I use the boron or gallium here, so again a 3 valence electron, so that will give me, so the boron, if it is diffused or implanted inside the silicon crystal lattice structure, it still forms the 4 covalent bonds. So 1, 2, 3 and 4, because silicon has 4 valence electrons, so it is likely to form the 4 bonds. But boron has one particular bond less, right? Or rather, the boron has 1 valence electrons less, so it still forms a covalent bond, but here it forms a hole. And we call it as a mobile hole in the sense whenever we apply the bias, this particular hole is a kind of moving towards the negative potential, right? And that's why it is called as a hole or a mobile hole. So that's about, so this p-type doping. So this is called as a p-type doping, the positive dopant. What it really means is, or what it really implies is, it's a, the p-type dopants will give us the positive majority carrier. So the holes are moving towards the negative terminal, and that's why we call it as a p-type doping. The last one was an N-type doping. Of course, the negative carriers, which is the electrons, which will be moving towards the positive potential, and hence it is called as an N-type doping. Right? Intrinsic concentration means it is the silicon which is not at all duped. right? It's a pure silicon material. So again, in this particular case, if I have a p-type dopant, one boron or a gallium atom which is doped inside the silicon crystal structure, I'll get one hole. So one hole acts like a majority carrier. And similarly, if I introduce 10 boron atoms, I'll get 10 such holes introduced into the silicon structure. And similarly, I can have 10 raised to 10 and above such concentration inside a 1 centimeter cube of silicon lattice structure. I'll get 10 raised to 10 and above such majority carriers, which we can use it to constitute the current or extract the current from the semiconductor material. Right, so let's move ahead. So in an N-type doped silicon crystal structure, so this is how the structure looks like. So the phosphorus atom, and then in the middle I have drawn the phosphorus atom. So because phosphorus has 5 valence electrons, I've taken that as an example for the N-type dopant. It forms the covalent bond, 4 covalent bonds. So phosphorus has 5 valence electrons, silicon has 4 valence electrons, so it forms the 4 covalent bonds, and it it has 1 electron here, which is a free electron. So that is what is stated earlier as well. And if I apply the bias here, so a bias of positive here and then a negative here, just a very simple theoretical understanding. So this free electrons now, due to this electric field of the positive and then the negative, the potential difference, this particular free electron will be forced to move towards the positive side, so the positive potential. Now what it really happens is the electrons will definitely move away, the free electron will definitely move away. But if you remember, the phosphorus earlier has 5 valence electrons, so the 5 electrons outside and 5 protons inside. Right, and when this particular free electron is moved away, so now we have the phosphorus atom which has 4 valence electrons outside and 5 protons inside. Thereby, this particular phosphorus atom is not electrically neutral anymore. Right, so it is now a positively charged atom. Right, so 5 protons and then 5 protons outside inside, and then 4 valence electrons outside. So that's why it becomes a positive atom. So generally we don't say, or we don't associate the positive charge to an atom, so it is called as an ion. Right, whenever the atoms become electrically charged, we call it as an ion. So now we call it as a phosphorus ion, which is a positively charged phosphorus ion. And we also say that because it's an atomic structure, it is not movable, so that's why we call it as an immobile positive phosphorus ion. Right, whenever we apply the bias here, the free electron is moved away, so we have this the positively charged phosphorus immobile ion. Right, so the electrons are taken away for extracting the current, whereas the atoms forms into an immobile positive ion. So similarly, if we have the phosphorus atoms which forms the positively immobile ion, similarly we have the boron, and whenever the bias is applied, so the boron, this particular holes will actually move towards the negative potential. Right, and thereby if the holes are moving away, what it really implies is whenever the holes are moving away, that means that the electrons in the any other or neighboring covalent bonds, right, they hop into this particular hole slot. So this electron is going to, just for a representation, I've taken this particular electron hopping into this particular hole space, and thereby it creates a hole here. So let me take a different color. If this electron moves away into this particular space, there will be a hole here, and I've just for the representation again, one another electron from this covalent bond will be moving to this to fill up this particular hole space. Thereby one more hole is formed here, and then this particular, similarly you will have this particular hopping here, so we will have one more hole here, and then this particular one hopping here or whatever. So finally I'll get a hole established here in this particular covalent bond, whereas it was actually started from the center one, but it moves towards the negative potential. So that's how applying the bias and having the electric field is actually trying to push these holes towards the negative potential. Right, so that is one way of representing. This is a very simplified way of representing the holes moving towards the negative potential. What it happens is, to this particular, the boron atom, there will be some kind of an implication. The boron atom, which was electrically neutral boron atom, now because it has 3 valence electrons outside and 3 protons inside, it is electrically neutral. But because of this particular electron coming in here and occupying the space of the holes, now outside the boron has 4 valence electrons and inside it has 3 protons, and thereby now this particular atom is not electrically neutral anymore, and thereby it is now a negative atom. Although whenever the negative or a charge, electrical charge is associated with an atom, we call it as an ion. So it is a negatively ion, and being an atom, it is not able to move, so we call it as an immobile negative boron ion. Right, very, very similar to that of the phosphorus, how the phosphorus or arsenic, whichever we have doped inside the silicon crystal structure, how it forms a positively immobile ion. Okay, so the last slide, what it talks about the dopant concentration. The dopant, although I have written it as the representation, this particular value of Nd and Na are nothing but the concentrations. Right, the concentrations are always given per unit volume. Right, so whenever we are diffusing to a block of volume, right, to a block of silicon volume, so per centimeter cube. And remember that the atom structure of the silicon has 5 into 10 raised to 22 atoms. Right, for a silicon, if I have a silicon block, and then if I take 1 centimeter cube of the silicon block, I'll get 5 into 10 raised to 22 atoms of the pure silicon. Right, so if I have a bulk silicon now, and then if I make it into 1 centimeter cube blocks, I'll get 5 into 10 raised to 22 atoms. But in this particular bulk silicon, if I do the diffusion or the implantation process, right, I'll be able to get the dopants inside the silicon bulk structure. And then if I do 1 centimeter cube of the blocks to be segmented out, then I'll get the concentration of the dopants inside 1 centimeter cube of the silicon, right, where we have 5 into 10 raised to 22 atoms of silicon. Right, so after the doping process is done, the diffusion process or the ion implantation process is done, we still have 5 into 10 raised to 22 atoms of silicon. In addition to that, we will have a dopant concentration. Right, so the dopant concentration, the overall process is actually characterized in terms of how many number of dopants have been introduced in 1 centimeter cube of the silicon structure. So that's why we have this particular the doping representation in terms of per centimeter cube. So we can introduce a maximum of 10 raised to 21. Right, it cannot be more than 10 raised to 22 because it will then destabilize the overall silicon structure. But we can introduce a maximum of 10 raised to 21, and we can go as low as 10 raised to 10. Right, 10 raised to 10 is how the intrinsic concentration will be, and we know that intrinsic concentration 10 raised to 10, the majority carriers, in the room temperature it will be broken, and then the bonds are broken, and then we'll get the majority carriers. But it's not so effective. So, right, so in that sense, from 10 raised to 10 to 10 raised to 21, we can actually do the dopants. So in this particular table, what I've stated here is the labelings, right? If I introduce 10 raised to 14 and less than 10 raised to 14, right? So that will be one kind of a dopant concentration. That is represented as N minus minus or P minus minus. So if it is a phosphorus atom, right, for example, the phosphorus or an arsenic atom with 10 raised to 13, right, with phosphorus or arsenic atom with 10 raised to 13 concentration, 10 raised to 13 phosphorus atoms I have introduced or I have diffused inside the silicon lattice structure of 1 centimeter cube. Then it is called as, or it is labeled as, or you can also say it as, it is annotated as N minus minus, right? And if it is a gallium or a boron, then we can say it as a P minus minus. Similarly, if the dopant concentration is somewhere between 10 raised to 14 to 10 raised to 16, right, 10 raised to 14 to 10 raised to 16, right, less than 10 raised to 16, then we will call it as N minus minus. So this one we call it as N minus, sorry, or P minus. So one negative less compared to the previous one where we had N minus minus or P minus minus whenever the dopant concentration was less than 10 raised to 14 per centimeter cube. And whenever it is 10 raised to 14 to 10 raised to 16, right, the dopant concentration is called as N minus or P minus. And we call it as N or P if it is in between 10 raised to 16 to and less than 10 raised to 18. Similarly, N plus or P plus if it is above 10 raised to 18 and less than 10 raised to 20. And if it is above 10 raised to 20, of course, we can go till 10 raised to 21. Above 10 raised to 20, we call it as N plus plus or P plus plus. Right, so whenever we see an N plus plus or a P plus plus, right, what we should recognize in the VLSI design or in the CMOS structure is that concentration is very, very high. It is about 10 raised to 20 per centimeter cube. So the diffusion process or the ion implantation process has introduced external atoms of either the phosphorus or arsenic or gallium or boron of about 10 raised to 20, which is very, very high. And if we see, if it is N minus minus, if we see somewhere N minus minus, then we should know that we should recognize it as a very low dopant concentration that has been introduced into the silicon structure.